Hi there. Firstly, let me apologise if there's any kind of noise in the background. I have a ceiling fan running and it's just way too hot in here to not have it going. So if that's causing some kind of background noise, I do apologise for that. Hopefully it won't be too bad. So on one of the Altair emulator videos I did a while back, there was a comment from a viewer called Benjamin who suggested that I do a Space Invaders emulator because it uses the same processor as the Altair. Now, I was aware of that, but the thought of actually emulating the Space Invaders original arcade cabinet, it had never occurred to me. And after I saw that comment, I thought, well, actually, that might be interesting. So I did a bit of research on the hardware and what needs to be done, and it didn't seem that it would be that difficult. Certainly not as difficult as the Altair or the Spectrum emulator. But I thought it should be challenging enough and should be interesting enough to do a video on. So here we are. So I've got a bit of information open here. This is some info on the hardware interrupts and things like that. I've also managed to locate the files that I'm going to need, and here we have the ROM images. There's 4 of them, and here are all the sound effects. Now the reason I've got the sound effects as WAV files and not actually emulating the sound hardware is there's no real need. The sound hardware is like a completely separate unit in the cabinet, and it's just activated by port out calls, and it just sits there doing its own thing. So, you know, there's no real need to emulate that. I can just play WAV files for each sound effect. Now that's going to cause complications later. C# at Visual Studio or .NET, whatever, although it has a audio playback system, sound player, it can't play more than one sound at the same time, and we're going to need that ability. So I'm going to have to use an audio package such as N-Audio, and I'm going to use N-Audio because I've used it before and I'm somewhat familiar with it. I'm sure there are probably other audio packages that will be more suitable, but I don't want to get into the learning curve of those. I just want to use things that I'm used to at the moment. There may also be something else in .NET that I could use as well that I'm not aware of. You know, .NET is a huge thing. Yeah, nobody knows everything about it. N-Audio is going to cause a problem because when you play a WAV file through N-Audio using it, it kind of plays the WAV file fine, but when it stops, there's a huge click that it puts through. So I'm going to have to deal with that as well. So let's take a look at what we need to do. There's a couple of interrupts, one on RST8 and one on RST10. One fires when the screen scan line is kind of in the middle, and one fires when it's finished. So that's when we're going to draw the screen, basically. The video is basically a standard resolution, 256 by 224, but it's rotated counterclockwise, so we're going to have to deal with that as well. And this seems to be fairly standard. We've got inputs. I don't think this one is used, so it says. So port 1 and port 2 deal with sort of the gain buttons and the dip switches. And output, as you can see, just sending an output will cause a sound to play. We've got a memory map in here telling us where we've got to dump the ROM files, and we have some dedicated hardware, and this is a shift register because the 8080 doesn't have a shift register. So what they've done, and I assume this is for moving screen data around more efficiently, is they've created a sort of discrete logic hardware shift register in the cabinet, and that's accessed via calls to input and output ports. But this doesn't seem too complex, so we should be able to emulate that. So there we go. Alright, here's Visual Studio. I've started the project, so let's get on with that. Let's rename Form 1. And this is YouTube screen size. This is rotated counterclockwise, so it's going to be in portrait mode, not landscape, so we're going to need to reverse those dimensions for the picture box. So let's drop a picture box in. So 224 by 256 is what we want. We'll drop a picture box on that, and size is 224 by 256, and that is very small, so let's double it. Okay, that's better. And what we'll do as well is we'll anchor that. Actually, I won't do that yet. Let's just arrange the window. I'm needing to put controls on the right hand side, so I'll leave a space for that. We'll change the background color of that so we know where it is. I think that should be enough space for the controls, and then we'll anchor this so it should resize itself as we resize the window. So let's just give that a go. Yeah. Okay. Now on this right hand side we're going to drop a panel, and we just want to anchor that panel. We don't want to anchor it to the left, but we want everything else. Then that panel should change. Yeah, there we go. So we'll call that P-box screen. What to call it? I'll just call it controls. So okay, and we can drop things into there that we need, such as dip switches and reset switch. I think that's probably all we're going to need anyway. We've got 8 dip switches, so let's drop those in. Okay, so there's all the dip switches. We're going to need a reset button as well, so we'll drop that in. So all of these need to fire an event. Now what I'm going to do is I'm going to attach it to the click event, not to the check change event. And the reason for that is I don't know if I'm going to need to programmatically change these checkboxes at some point if I put some settings file or something in there. And I don't want a programmatic change of the dip switch to fire the event. I only want the event to fire if the user actually clicks it. So I'm going to add it to the click event. And this is just going to be dip switch. There we go. And also we want an event when we click reset. So let's get the processor code in there now. So there's a shortcut on the desktop to that project, and we're going to copy our 8080 code into there. So I'll just copy my namespace over, and I don't need all this custom controls and project or Altair 8800. I just need the Intel 8080 and the monitoring packages that needs. Delete those. And the monitor is just like a disassembler and just support code for the processor and for numbers of other things. But yeah, those are the two namespaces I'm going to need. So let's include those into our project now. Okay, to do this, we'll go to YT Invaders. We'll add an existing item. Go into here and add the processor code, and also add the monitor code. We've got build failed. Oh, I need to didn't include the disassembler, did I? Disassembler. So this isn't really ideal, just copying files around like that, but I want this to be sort of self-contained, so it'll do for now. Alright, I'm going to create a new class. I'm going to call this core, which is going to be the core of the Space Invaders emulation. Let's do the constructor first. So I'm going to need, I want to pass in the screen, so that's going to be the picture box. Okay. Set that. Make that read only because it's set in the constructor. So in UI, we'll set a shown event to create that. So we'll go down to shown and create a field for it, and then core equals new core P-box screen. So let's start working on some of this hardware. What should we do? Let's do the dedicated shift hardware. So it looks like what we got. We've got writing to port 4. So we've got setting an offset. We've got writing a byte to the shift register, and we've got reading it. So let's do set offset first. So we're going to need shift register offset. And we use ints for everything. So shift reg offset. Set that to 0 initially. Set shift reg offset. And this is just going to be an int. So that's just a question of setting this value, but it can only go from 0 to 7. So we need to trim that to the last 3 bits. So our shift register offset is going to be equal to offset and 0x. first 3 bits, so that's 7. Now we need to actually have a shift register. So shift reg, so that's a 0 initially. Private void and write shift register with the value, and when we write it, puts it into, okay, so this part moves into that part, and then this goes into there. Okay, looks like the shift register itself needs to scroll right by 8 bits, and then we need to put value into the upper 8 bits of shift register. So shift register, we're going to order that with value, which is bit shifted left by 8. That should do that. But what I'll also do here, just for, is trim that so we don't get any junk anywhere else in the end. Now reading the shift register, that depends on the offset. Okay, so private int read shift register, and that doesn't have any parameters. Shift it, so if the offset is 0, we're shifting right by 8 bits. If the offset is 2, we're shifting right by 6 bits. So it's basically 8 takeaway offset. Right, okay. So we're returning the shift register, and that's shifted right by 8 minus shift reg offset. So there's the methods in place for dealing with the shift register. We'll just call those from the port commands. What else we got here? I think that's about it. We just need to set up, oh, of course this core needs to implement my 8080 code, so we'll do that. So we've got the port in, read byte, write byte. So we need to set up some RAM. Now the RAM is 4000 hex long. So when we read a byte, we've also got a RAM mirror. Oh, yeah, so it's mirrored in higher areas of RAM. It will just show you what's in the lower areas. So when we read a byte and when we write one, we're going to trim that to 3FFF, and that will deal with the mirroring. Now we need to return it, but we've got ROM areas. All we need to do here is return RAM. Now writing, we need to check to make sure we're not writing over ROM. So ROM ends at 2000. So okay, if address is greater than or equal to 2000 hex, then we can actually set it. So RAM ADDR is equal to val. That needs to be a byte, of course. Now something else we need to do here that I'm thinking we should do is we'll intercept any writes to the video RAM and deal with that separately. Anything over 2400 hex. If address is greater than or equal to 2400 hex, then let's create another, let's just say screen RAM update, and we'll pass the same values, so address, and we'll call that here. So screen RAM update address value. Then any call to video RAM, we can just draw that straight away, because all we're going to do is take whatever we've drawn over that period. When the vertical blank occurs, we'll just update that onto the screen. We're going to need to fill the ROM area. Let's copy our files that we're going to need. I'm just going to dump them in the debug folder. Okay, we'll just dump them in there so they're easy to access. Okay, so we've got E, F, G, and H. So our ROMs, where do they go? Oh, here we go. Okay, let's put those in. So you can use array copy for this. And source array is going to be file. So read all bytes, and we're reading, what's it called? Invaders H. So source index, we'll go from 0 obviously. Destination array, that's going to be RAM. Destination index in this case is 0. Yeah, they're all 800 hex. So 800 hex, and then we need 4 of those. Okay, and each of these goes into higher areas of ROM. Okay, there we go. So that's the ROM sorted out. So the screen, as bytes come in, we need to figure out how to update that. So what I'm thinking is we'll make an intermediate bitmap. So this is basically the buffer, And this is the same size as the screen, so that's 224 by 256. Okay. So down here we need to figure out, let's forget the screen rotation for the time being, and let's figure out what our X and Y coordinates are for the address that's come in. So the address starts at 2400, so let's reduce that. So let's take away 2400 hex so that the actual value we get put into RAM update is from 0, right? So that makes it easier. So remember, what's coming in is a byte, not a pixel. So, and each byte is 8 pixels because it's a bit mapped image. If we want to work out the line that we're on, so obviously a line is only 1 pixel wide, or high, I should say. Now across the screen, remember we're not rotating at the moment, across the screen is 256, and there are 32 bytes in a line, right? Because it's 256 across, 256 divided by 8, because there's 8 pixels, that's 32 bytes on each line. So to get the line, or the Y value, is just going to be the address divided by 32, right? Now our X value, which is across, the X value is essentially the remainder from this, right? So it's going to be address modulo 32, but remember that there's 8 pixels in each byte, so we need to multiply that by 8 to get it into pixel dimension. Now I'm pretty sure the compiler will pick this up and change it to more efficient code, but we're going to do it here. So dividing by 32 is effectively the same as bit shifting. So we can bit shift this right by 5 bits. That's the same as dividing by 32. Now getting the modulo, so 32, 64, 128, 16, 8, whatever. Now 32 is a bit mask of 1F, so we can just go and 1F, and that will do the same thing as mod 32, but it only works with those kind of numbers. Yeah. And again, we're multiplying by 8, so that's the same as bit shifting left by 3. So that just makes that code more efficient. But like I say, the compiler should pick that up. It should notice things like that and do it automatically, but let's just make sure. But remember, the screen is rotated, right, by 90 degrees counterclockwise. So that's going to invert our X and Y. So this becomes X and this becomes Y. If you think about it, we're scanning from left to right, okay? If we rotate that whole thing counterclockwise by 90 degrees, we're scanning from bottom to top. And the bitmap is from top to bottom, yeah? The numbers go up top to bottom. So we need to invert the Y-axis. All we need to do is take it away from our vertical height, but remember we're counting from 0 to 255, so we'll just take the whole thing away from 255 and that will invert our Y-axis. So that basically translates our address into an X and Y coordinate which is rotated counterclockwise by 90 degrees. So all we need to do now is set that pixel, or set those 8 pixels depending on what our value is. Now, if you look here, the screen geometry, it starts from the least significant bit going to the most significant bit. So for int bit is equal to 1, because that's the first bit, is less than or equal to 128 for the last bit, and we'll shift it left by 1 bit. So it's X and Y, so we're going to say, so screen buffer set pixel, and we're setting X comma Y, and we're going to set it depending on whether the bit in val is set. So that's going to be bit and val is not equal to 0. So if it's not 0, then it's a 1, so we're going to color it white. Otherwise we're going to color it black. So this is only going to create a black and white image for now. We'll deal with the coloring, the color bands later, but that should set the screen up and draw the screen as writes to screen memory occur. Let's just get rid of these exception throwers. I'm just going to return 0 here. Okay, so what about some ports? I think port 0, that doesn't matter, but we've all, okay, well, we may as well implement it. So we're going to switch on the port, case 0. Now this doesn't appear to be used, and it's bit 1, 2 and 3 are always 1, and I think we can forget the rest. So that's 14. Okay, so we can just return 14 there, right? Okay, port 1. The only thing that's set always is bit 3. So that's 1, 2, 4, 8. So we'll just return 8 there. We'll deal with the dip switches and buttons later. And port 2, we can just return 0. But let's do this a little bit more cleanly. So default return 0. Get rid of the unreachable code there. Okay. So that's sort of prototype port in. So what about port out? We're not going to implement anything sort of sound or anything yet, but we do need to implement the shift register. Yeah, and port 3 on input is also the shift register. So first of all, looks like port 2 sets the shift offset. So let's again switch on the port. Case 2 sets the offset. So we've already got that. Set shift reg offset with value. Case, I believe it was 4, right? Right into port 4, yeah. So 4, and this is going to be write shift register with the value, and reading it is port 3. So case 3, and we're returning read shift register. All right, we've not done the interrupts yet, but we should have enough for a basic initialization of the console, I think. So let's start the CPU. So CPU start. Now that only puts it in a start condition. It doesn't actually start it running because it's got to deal with, you know, stepping and things like that. So we have to also say run. Now that's going to be filling the screen buffer, but we're not going to be able to see that. So we're going to need something to do that. How about, because this is going to be drawn with the interrupts, I've not implemented those yet. So how about if we just temporarily make a counter here? So int counter equals 0. If the counter is greater than, let's say, 100, so after every 100 calls to that, we'll reset it to 0, and then we'll dump the screen buffer into the bitmap. PB screen, we need to invoke, and we can just simply drop the screen buffer into, in actual fact, I think we ought to clone it. So let's make a clone of it here, and then we can drop the clone into the image. So PB screen dot, we use the background image, equals clone. And we should be okay with disposing of that, because I think the .NET system, when you start messing with images of picture boxes, it deals with disposing of it for you. So that should be okay. Another thing I haven't done, I need to set the background image layout here to zoom so that it will change its size. Zoom. Obviously it's not going to work, but hopefully we'll get some image displayed. So let's see what we do. Okay, nothing happening there. Count plus plus. Yeah, it's not incrementing the counter. Okay, let's try again. Ooh. Okay, well, it's doing something. Oh, right, we're skipping. We need to draw in between the lines, right? So each time a bit increases, we're increasing the, so remember it's rotated, so each bit we need to decrease y by 1 each time, so it scans up. Okay, let's see if that makes any difference. Oh, there we go. Okay, let's implement this reset button while we're here. So let's put in a reset command, public void reset, and this is just going to be I'll do a soft reset. Okay, button reset, click, call, reset game, because we're going to need that for changing the dip switches. You see, you change the dip switches, you need to reset the system. Okay, so we're going to need to set up the interrupts. It's basically a timer interrupt. When all said and done, it's timed on the screen, but obviously we haven't got a CRT on this, so we're going to have to emulate that. We've got two interrupts, one that occurs at the middle of the screen and one at the end. So we're running at 2 megahertz. So 2 megahertz and it's 60 frames a second. So if we divide that by 60, that's 33,333 T-states for every interrupt. But they're occurring offset from each other. So 16666. Okay, so let's set up the interrupts. Remember what I called this now for timer interrupts. Set T-state interrupt timer. Okay, so delay. This is the amount of T-states that it will execute before it actually starts doing it. So we'll put a delay in here of 33,333, and the period again is 33,333. That's how many T-states before it occurs again. Vector. So we'll make this one the end of the screen, right? So that is RST10. RST10 is opcode D7. So that's D7. And we are going to need an action with that, but we won't do that just yet. And we also need to set up another timer, but this time we want this to occur sort of in between the other one. So we'll set the delay for this to 16666 and the same period. And this one has a different opcode, which is CF. Okay, so that's CF. Now we can get rid of this silly timer thing here. Probably should have saved that code. All right. So private display screen. Okay, so we're just doing what we did before. Okay, and that will display the screen. And that is the action we need to perform on the VBlank, which is this one. So it's going to be display screen. And what that does, it just executes that action before it actually fires the interrupt. Now we've got the interrupt set up, the game should technically start to run, I hope. So let's give it a go. Yes, there we go. We've got no colours, obviously. Okay, that seems to be working. I'm noticing it's a little tiny bit jerky, and that's because of the timing that I'm using. I could improve that, but that's a rabbit hole you can go down forever. So, you know, it's going to be a little bit jerky. Going to have to live with it. Okay, I'm going to take a break at this point.